displays are easy to understand. A screen lights up pixels, images appear, and your brain fills in the rest. But the display inside the Apple Vision Pro headset operates at a very different scale. Instead of large panels like televisions or smartphone screens, the Vision Pro uses Micro-OLED displays. Each display is about the size of a postage stamp, yet it contains millions of pixels. Packing that much resolution into such a tiny surface requires a different manufacturing approach. Traditional OLED screens are built on glass panels. Micro-OLED displays are built directly on silicon wafers, similar to how computer chips are manufactured. This allows far higher pixel density than conventional displays. Pixel density becomes critical in head-mounted displays. When a screen sits only a few centimeters from your eyes, individual pixels can become visible. This produces the screen door effect that many early virtual reality headsets suffered from. Micro-OLED reduces that problem dramatically. By shrinking pixels and increasing their density, the display can produce extremely sharp images even when viewed at very close distances. But resolution is only one part of the equation. Brightness also matters. Headsets must generate enough light to remain visible, even when optical lenses and display layers absorb some of the output. Micro-OLED panels must therefore produce high brightness while maintaining efficiency. Generating bright images at small scales introduces heat. As electrical current flows through the OLED materials, energy converts into both light and heat. In compact electronics like headsets, thermal management becomes important. Too much heat can reduce display lifespan or affect nearby electronics. Power consumption becomes another constraint. Unlike televisions connected to wall outlets, headsets operate on batteries. The display system must balance brightness, refresh rate, and energy efficiency to maintain usable battery life. Higher refresh rates improve motion smoothness, but increasing refresh rate means pixels must update more frequently, which increases power demand. Manufacturing complexity also plays a role. Because Micro-OLED panels are built on silicon wafers, the production process must meet extremely tight tolerances. Any manufacturing defects can ruin entire sections of the wafer. That makes these displays expensive to produce. Engineers must balance cost, resolution, brightness, and reliability while keeping the device compact enough for comfortable use. Then there is optics. The Vision Pro uses a complex lens system to project images from the small displays into the user's eyes. These lenses must enlarge the image while maintaining clarity across the field of view. Optical distortion must be corrected through both lens design and software processing. Tracking technology adds another layer. Eye-tracking cameras inside the headset detect where the user is looking. The system can then prioritize rendering detail in that specific region, reducing unnecessary processing elsewhere. This technique, known as foveated rendering, helps improve efficiency. All of these systems work together to create the illusion of a digital environment occupying real space. Displays generate the image. Optics project it correctly. Sensors track user movement. Software coordinates everything in real time. The Micro-OLED display may look like a small component inside the headset, but it plays a central role in making spatial computing believable. Because when pixels become small enough and sharp enough, the technology begins to disappear. And when the technology disappears, the experience takes over.